What's up is down, what's left is right. Chasing stars and...
Hello my friends and welcome back to the Forging Titans.
Steel forging is one of the most remarkable manufacturing processes, transforming raw metal into highly durable and precisely shaped components. This technology is crucial in industries where strength, durability, and precision are paramount, such as in the production of train wheels. Among the global leaders in steel forging, China stands out not just for its scale but also for the advanced levels of technology it employs in manufacturing, particularly in the field of train wheel production. Steel forging involves heating a piece of steel to a temperature where it becomes malleable and then using compressive forces to shape it into the desired form. This process significantly enhances the material's strength by aligning its internal grain structure, which is particularly important for components like train wheels that must endure extreme stresses and loads. Modern steel forging technology has advanced significantly, incorporating precise temperature controls, automated hammering and pressing machines, and sophisticated quality control systems. For instance, the use of closed die forging in train wheel production ensures that the wheels are not only strong but also have the exact dimensions and surface finish required for high-speed rail applications. The forging process can produce train wheels with diameters ranging from 500 mm to over 1,200 mm, depending on the type of train and its operational needs. China's manufacturing prowess, particularly in the field of train wheel production, is nothing short of extraordinary. The country has invested heavily in state-of-the-art manufacturing facilities that leverage the latest in forging technology. For example, the Taiyuan Heavy Industry is one of the world's largest train wheel manufacturers, capable of producing over 2 million wheels annually. This facility alone can produce wheels for everything from high-speed trains to heavy freight locomotives. China's train wheel production is marked by several impressive technological achievements. The forging processes used are not just about sheer scale but also precision. China's manufacturers utilize computer-controlled hydraulic presses with capacities exceeding 10,000 tons, ensuring that each wheel is forged to exact specifications. The process also includes induction heating systems that can rapidly bring the steel to the necessary forging temperature, reducing energy consumption and improving overall efficiency. One of the key indicators of China's technological superiority in this field is the quality of the final product. Chinese-made train wheels are renowned for their durability and precision, often surpassing international standards. For example, the wheels produced by Chinese manufacturers typically have a hardness level of around 320 to 380 HB, Grinnell hardness, which ensures they can withstand the rigorous demands of high-speed rail travel. Additionally, China's adoption of automation in the manufacturing process has led to significant improvements in productivity and quality control. Advanced robotic systems are employed for tasks such as die handling and forging, which not only increase the speed of production but also reduce the margin for error. This automation allows for consistent production of train wheels with very tight tolerances, often within plus or minus 0.1 millimeters, which is crucial for maintaining the balance and stability of trains operating at speeds exceeding 350 kilometers per hour. The train wheel manufacturing process begins with the use of high-quality steel produced at Lucchini RS's Lovere plant in Italy. The process starts with the formation of ingots, which are then cold cut to prepare them for further processing. Ingot sections are heated in a specialized rotating furnace with a 23-meter diameter, capable of producing 40 tons per hour. Next, the heated ingots are subjected to a 9,000-ton hydraulic press, followed by a precise rolling operation in a mill equipped with 13 computer-controlled axes. This integrated production process, without intermediate warehousing, allows for a production rate of up to one wheel every 58 seconds. This modern rolling mill has a maximum annual rolling capacity of approximately 260,000 wheels. This rolling mill ensures that the wheels, which can range up to 1,450 millimeters in diameter, are formed accurately. A subsequent 5,000-ton press further refines the wheel shape. After pressing, the wheels undergo heat treatment in specialized furnaces and tanks to enhance their strength and durability. Sandblasting is then performed to clean the wheel surfaces before they are meticulously inspected. Machining follows to achieve the final dimensions and surface finishes required for optimal performance. A second inspection ensures that each wheel meets strict quality standards before it is prepared for shipment. Using advanced CNC machines, the wheels undergo processes such as turning, drilling, and grinding to ensure precise geometries, smooth surfaces, and accurate fit with other components. This step is crucial for the wheel's functionality and safety in demanding rail environments. Following machining, the wheels are assembled with axles to form complete wheel sets. This assembly process involves press fitting the wheel onto the axle with high precision to ensure proper alignment and balance. After assembly, the wheel sets are painted with a specialized coating that protects against corrosion and wear. The paint not only enhances the durability of the wheel sets but also gives them a finished appearance. Next, we will visit the Indian Railways factory. The manufacturing of cast steel wheels at here involves a precise and technologically advanced process. The process begins with the selection of high-quality scrap steel, which is melted in electric arc furnaces to achieve the desired chemical composition. This molten steel is then poured into preheated ladles and transferred to the molding section. The key technique used in the casting process is the bottom pressure pouring method, where molten steel is introduced into graphite molds under controlled pressure. This technique, employed at facilities like the Rail Wheel Plant, RWP, in Bella, Bihar, ensures uniform filling of the mold, reducing defects and enhancing the structural integrity of the wheels. Once the steel is poured and solidified in the molds, the wheels are carefully extracted and subjected to heat treatment processes, including normalization and tempering. These steps are crucial to achieving the required hardness, toughness, and mechanical properties that ensure the wheels can withstand the rigorous demands of rail service. Following heat treatment, the wheels undergo machining to achieve the precise dimensions and surface finish necessary for their application. This includes turning, drilling, and finishing processes. Each wheel is then subjected to stringent quality checks, including ultrasonic testing, hardness testing, and dimensional inspections to ensure compliance with Indian Railways standards. Open die forging is a widely used manufacturing process for producing train wheels due to its ability to create high-strength components with superior mechanical properties. However, like any manufacturing process, it has its advantages and disadvantages compared to other methods such as casting, closed die forging, and rolling. Below is an analysis of the pros and cons of using open die forging for train wheels. Advantages of open die forging. Superior mechanical properties. Open die forging produces train wheels with excellent mechanical properties, including high tensile strength, toughness, and fatigue resistance. These properties are critical for train wheels, which are subjected to extreme loads and stresses during operation. The process aligns the grain structure of the metal, leading to improved strength and durability. For example, the tensile strength of forged train wheels can reach up to 900 megapascals, significantly higher than cast wheels, which typically exhibit tensile strengths around 600 megapascals. Material efficiency. Although open die forging involves significant material waste compared to closed die forging, it offers better material utilization than casting. The process minimizes defects like porosity and inclusions, which are common in cast components, leading to a higher yield of acceptable parts. The material yield in open die forging can be around 70 to 85%, compared to approximately 55 to 70% in casting. Flexibility in production. Open die forging is highly adaptable and can accommodate various sizes and shapes of train wheels without the need for specific dies or molds. This flexibility makes it suitable for low-volume production or custom wheel designs. In contrast, closed die forging requires dedicated tooling, which is costly and time-consuming to produce, especially for small batches. Cost-effectiveness for large components. For large train wheels, open die forging can be more cost-effective than closed die forging or rolling, especially in terms of tooling costs. The absence of specialized dies reduces the upfront investment, making it an attractive option for producing large, low-volume components. Disadvantages of open die forging. Lower dimensional accuracy. Open die forging typically results in lower dimensional accuracy compared to closed die forging and rolling. The lack of precise dies means that additional machining is often required to achieve the final dimensions and surface finish of the train wheels. This extra machining can increase production costs and lead times. In contrast, closed die forging can achieve near-net shape parts with minimal machining required. Higher labor and energy costs. Open die forging is a labor-intensive process that requires skilled operators to control the forging process. Additionally, the process consumes more energy due to the repeated heating and deformation steps needed to shape the metal. Energy consumption in open die forging can be 30 to 50% higher than in rolling processes, leading to increased operational costs. These ingots are first subjected to a cold cutting process, where they are cut into sections of appropriate length for axle production. The sections are then transferred to a heating furnace, where they are heated to the desired forging temperature. Once the steel reaches the required temperature, it is moved to a 1,000-ton press, where the ingot sections are forged into rough axle shapes. The high pressure ensures the material is evenly distributed, resulting in a robust and durable axle. Following the forging process, the axles undergo heat treatment in specialized furnaces to enhance their mechanical properties, including strength and toughness. The heat treatment involves controlled heating and cooling cycles, which are followed by quenching in heat treatment tanks to achieve the desired hardness and structural integrity. After forging and heat treatment, the axles are ready for machining, which involves multiple steps to achieve the final specifications. The process begins with loading the forged axles onto a machining center, where they are securely positioned for precision work. The first machining operation is end-facing, which involves cutting and finishing the ends of the axle to ensure they are perfectly square. This is followed by roughing, where the axle surface is machined to remove excess material, bringing it closer to its final dimensions. Next, finishing operations are performed to refine the axle surface, achieving the precise dimensions and smooth finish required for its application. Cold rolling is then used to strengthen the axle surface by deforming it slightly, increasing its fatigue resistance. The machining process continues with 2 stages of grinding. Grinding 1 is a rough grinding step that ensures the axle's diameter is within the required tolerance. Grinding 2 is a finer operation, providing a smooth, polished surface. After grinding, the axle undergoes washing to remove any residual machining debris. Following the cleaning process, a dimensional check is performed to ensure that all measurements meet the required specifications. The axle is then subjected to a magnetic test to detect any surface or subsurface defects. Once the axle passes these quality checks, it is marked and labeled for identification, followed by ultrasonic testing for internal flaws. Finally, the finished axles are unloaded and prepared for shipment or further assembly. The mounting of a rail wheel onto an axle involves a precise and reliable process known as press fitting, widely used in the manufacturing industry for its strength and efficiency. In this process, the wheels are press fitted onto the axle from both ends, forming a secure wheel and axle assembly. Press fitting relies on an interference fit, where the wheel's bore is slightly smaller than the axle's diameter. The assembly process involves applying a significant force to push the wheel onto the axle, creating a tight fit through friction. This method ensures that the wheels remain securely attached during the rail vehicle's operation, preventing slippage that could lead to derailments or other safety issues. The quality and reliability of the press fit are critical, and they can be verified through press fitting curves, which monitor the force applied during the assembly. These curves help ensure that the assembly falls within the acceptable limits set by standards such as the European standard N13260. Additionally, finite element analysis (FEA) tools like Abacus are used to simulate and predict the stress distributions and maximum press fitting forces, further ensuring the integrity of the assembly. A well-executed press fit provides a strong, durable connection between the wheel and axle, capable of withstanding the high torques and stresses experienced in railway operations. This process is a cornerstone in ensuring the safety and longevity of railway wheelsets. Danobat Automatic Triple Nut Runner for Railway Wheelset is a precision machine designed for efficient mounting of bearing end caps onto railway wheelsets. It operates through a PLC-controlled system that automates the entire assembly process. The machine positions the end caps, which consist of an end cap, a lock tab, and 3 bolts, on the wheelset. The wheelset is then loaded into the machine, where the axial positioning of the bolt heads is measured. The machine automatically aligns the bolt heads and clamps the end cap in place, then uses 3 sockets to simultaneously tighten or loosen the bolts, ensuring uniform torque application. The system also checks for non-broken bolts and can perform simultaneous loosening if both bolts are aligned. This process ensures precise, consistent, and reliable assembly, enhancing the efficiency and safety of railway wheelset production. This CNC-controlled portal lathe for railway wheelset turning is a high-precision machine engineered for the maintenance and reprofiling of railway wheels, as well as brake disc machining. This machine is essential for maintaining the operational integrity of railway locomotives, coaches, and wagons by ensuring their wheelsets remain in optimal condition. The portal lathe is built with advanced smart manufacturing technology, allowing it to deliver high-accuracy machining for wheel reprofiling and brake disc turning. This technology is crucial for adapting to varying cutting conditions in real time. The lathe can automatically adjust the cutting speed and conditions during the machining process without the need for human intervention. This adaptive capability enhances throughput by speeding up operations under favorable conditions and slowing down when necessary to protect the machine and prolong its lifespan. The machine is designed with a user-friendly programming interface that guides the operator through the sequential steps of the machining process. This is supported by centralized information access, which simplifies operation and reduces the learning curve for users. Additionally, digital apps integrated into the system provide valuable features such as alarms, troubleshooting, and a preventive maintenance plan, all of which contribute to minimizing downtime and optimizing machine performance. The portal lathe comes in 2 main configurations, the roller type and the jaw type. This flexibility allows for customization to meet specific operational requirements. The machine is capable of handling various tasks related to wheel machining, including measuring the wheel's rolling profile, the inner side of the wheel, the external face, and the end-of-life groove. It also efficiently performs brake disc machining, which is essential for maintaining the braking system's effectiveness. To further boost production capacity and reduce manpower requirements, the machine can be equipped with automation features, particularly for loading and unloading operations. This automation is especially beneficial for users for whom throughput is a critical metric, as it significantly enhances the machine's productivity and efficiency. The railway industry has long been a backbone of global transportation, facilitating the movement of goods and passengers over vast distances. Within this vast network, the repair and maintenance of railway wheels represent a critical subset of the industry, essential for ensuring the safety, reliability, and efficiency of train operations. The importance of this sector cannot be overstated, as any failure in wheel integrity can have catastrophic consequences, leading to derailments, significant financial losses, and even loss of life. This article delves into the intricacies of the railway wheel repair and maintenance industry, highlighting its processes, challenges, and future prospects. The scope and scale of the railway wheel market. Railway wheels are subjected to immense stress, bearing the heavy loads of trains and enduring constant friction against the rails. Globally, the railway wheel market is substantial, reflecting the sheer number of trains in operation and the essential role these wheels play in the overall rail infrastructure. In Europe, the International Union of Railways, UIC, reports that there are over 1.7 million freight wagons and 280,000 passenger coaches in operation. Each of these vehicles typically has multiple wheels, and the demand for repair and maintenance services is consequently high. The situation is similar in the United States, where the Association of American Railroads, AAR, estimates that over 1.6 million freight cars are in service, with each car typically equipped with 8 wheels. Given the average lifespan of a railway wheel, which ranges from 5 to 10 years depending on the level of use and maintenance, the need for regular and meticulous maintenance is constant. The importance of maintaining these wheels cannot be understated, as they play a crucial role in ensuring the safe operation of trains. Any compromise in wheel integrity can lead to accidents, which are not only costly but also dangerous. As a result, the railway wheel repair and maintenance industry has become a vital part of the broader railway sector, with a range of specialized companies dedicated to this critical task. Key processes in railway wheel maintenance. The maintenance of railway wheels involves a variety of specialized processes, each aimed at preserving the functionality and extending the lifespan of the wheels. These processes include regular inspections, reprofiling of wheels, bearing replacement, and the application of heat treatment and stress relief techniques. Regular inspections. The foundation of effective wheel maintenance lies in regular inspections, which are essential for identifying early signs of wear and tear. These inspections typically focus on detecting flat spots, cracks, and other forms of damage that can compromise the integrity of the wheel. Ultrasonic testing is a widely used method in this regard, as it allows for the detection of internal defects that may not be visible on the surface. According to the UIC, conducting regular inspections can reduce the risk of wheel failure by up to 50%, highlighting the importance of this preventive measure. Wheel reprofiling. Over time, the tread of a railway wheel wears down due to the constant friction it experiences while in service. This wear can lead to a loss of the wheel's original profile, which is crucial for maintaining proper contact with the rail. Reprofiling involves machining the wheel to restore its original shape, ensuring smooth and efficient operation. This process can be carried out using underfloor wheel lathes or more advanced CNC, computer numerical control, machines. The UIC estimates that regular reprofiling can extend a wheel's lifespan by up to 30%, making it a cost-effective maintenance strategy. Bearing replacement. Bearings are an essential component of the wheel set, allowing the wheels to rotate smoothly and with minimal friction. However, bearings can wear out over time, and if not replaced promptly, they can lead to serious issues, including derailments. The AAR has identified faulty bearings as one of the leading causes of wheel-related derailments, underscoring the importance of regular bearing inspections and timely replacements. Heat treatment and stress relief. Railway wheels are exposed to significant thermal stress during operation, particularly during braking. This can lead to the formation of micro cracks and other forms of material fatigue over time. Heat treatment and stress relief processes are employed to mitigate these issues, extending the operational life of the wheels and ensuring they remain safe to use. Challenges facing the industry. Despite its critical importance, the railway wheel repair and maintenance industry faces several significant challenges. These include the high cost of advanced equipment, a shortage of skilled labor, and the increasing complexity of modern railway systems. Addressing these challenges is essential for ensuring the continued effectiveness and efficiency of wheel maintenance operations. High equipment costs. The machinery and equipment used in railway wheel maintenance are highly specialized and, as a result, can be extremely expensive. For instance, a high-quality CNC wheel lathe, which is essential for reprofiling wheels, can cost upwards of $500,000. Similarly, an ultrasonic testing system, which is used for detecting internal defects in wheels, can range from $100,000 to $300,000. These high costs make it difficult for smaller operators to compete with larger, well-funded companies, leading to a concentration of the industry in the hands of a few key players. Skilled labor shortage. The railway wheel repair and maintenance industry relies heavily on skilled technicians who are capable of performing tasks such as wheel reprofiling and bearing replacement. However, there is a growing shortage of qualified labor in this field, particularly in developed countries. According to the AAR, the average age of railway maintenance workers in the US is over 50, indicating a looming retirement crisis. Attracting and training new talent is therefore a critical priority for the industry. Increasing complexity of modern railway systems. The railway industry is constantly evolving, with new technologies and systems being introduced to improve safety and efficiency. However, these innovations also add complexity to the maintenance process. Modern trains are equipped with advanced braking systems, real-time monitoring technologies, and other sophisticated systems that require specialized knowledge to maintain. This increases the time and cost associated with wheel maintenance and places additional demands on the skills of technicians. Market size and future growth prospects. The global railway wheel repair and maintenance market is substantial and is expected to grow steadily in the coming years. According to a report by Markets and Markets, the market was valued at approximately $3.1 billion in 2022 and is projected to reach $4.6 billion by 2027, growing at a compound annual growth rate (CAGR) of 8.1%. Several factors are driving this growth, including the increasing demand for rail transportation, particularly in emerging economies, where infrastructure development is a key priority. One of the key trends influencing the market is the shift towards high-speed rail. High-speed trains place greater demands on wheel sets due to their higher operating speeds and the increased forces they generate. As a result, the wheels of high-speed trains require more frequent maintenance and the use of advanced materials and technologies. This trend is expected to drive demand for specialized wheel maintenance services in the coming years. Additionally, the adoption of electric trains is likely to further fuel the growth of the market. Electric trains are generally more environmentally friendly and efficient than their diesel counterparts, and as more countries look to reduce their carbon emissions, the shift towards electrification is expected to accelerate. This, in turn, will create new opportunities for companies in the railway wheel repair and maintenance industry.